Hello everyone, welcome to this lecture of the course Digital Electronics and Circuits. In the past couple of lectures, we have looked at registers and counters, and we looked at various variations of both registers and counters. To capture all these variations, we started with the registers, right? We looked at two circuits. One was without load operation where output was transferred directly to input. One was with load. And once we had with load, right, we saw two variations of this particular circuit. One was clock gating, where we gated the clock, and one was with parallel load. Once we looked at register, right, after this, what we did was we saw a specific kind of a register called as a shift register, where we have serial input and we were able to right shift or left shift the output, right? Once we were done with registers, we looked at counters, and counters we said were a special kind of registers. We looked at two kinds of counters. One was a ripple counter, where output of one flip flop act as a clock for triggering another flip flop, and another was synchronous counters, where all the flip flops had the same clock pulse for driving the logic. Correct. In this particular lecture, we will talk about two special type of counters. One is called a ring counter and other is called a Johnson counter. Let's discuss these two kinds of counters, and we will look at the applications of these counters as well. Right. If we have to begin with a ring counter, right, let's recall what we looked at for a shift register. For a particular shift register, if you recall, what we had was we had 4D flip-flops in a back-to-back mode, right? So this is I'm drawing a diagram of shift register which we discussed in the register lecture. All of these had a clock connected to same clock. This was also connected to same clock, same clock, same clock. Right? All of them were connected to same clock, and what we had was, if you recall, we had a clear input, which was connected to the reset pin of the flip-flop everywhere, right? And once we had this, what we did on shift register was output of one flop, this was Q, we connected to input of the another. Right? And what we said was, let's assume this is our counter QA. Let's give a nomenclature QB, QC, and QD. Correct? What we said was we will have a serial input SI, and what would happen is if the input is QA, QB, QC, QD is the present state, the next state would be equal to SI, QA, QB, QC. So basically we had a right shift operation over here, assuming QA is the MSB, correct? Now in this particular case, right, if we do a variation, and if the variation is such that instead of supplying a new input SI, we connect output of the last flop to the input of the first flop, which is something like this. We feed it back to here. This particular variation of shift register is called as a ring counter, right? And we will see why it is called as a ring counter, right? Let's assume that what we have over here is in the initial state, right? What we do is when we set clear is equal to 1, all the outputs over here. If we tap output over here, tap output over here, tap output over here, tap output over here, QA, QB, QC and QD would be equal to 0 0 0 0 0. Once we do this clear, we install clear is equal to 0, and let's assume that at time t equal to 0 we supply a value over here, right? We supply a value 1, we put a 1 over here, right, such that dA is equal to 1. And once we are done with this, right, we remove this load operation, we remove this load value of 1 before first clock edge. What would happen in this particular case is this particular value of 1, right, now we will have an input of 1 0 0 0. What would happen at the next clock edge is this one would get transferred to this QB output, right? So basically, if we have to write it down over here, at time t equal to 0, we made initial state as 1 0 0 0. At time t1, this one would get right shifted at the so when I say t1, it's like a clock edge. So this one will get shifted over here, and this 0 will come back as an input, right? So 0 1 0 0. Similarly, at the next passage, which is time t2, this one will again get shifted, 0 will get shifted over here, 0 0 1 0. At time t3, which at the next clock edge, 0 0 0 1. And now what will happen at time t equal to 4? This one will get shifted over here, we will get 1 0 0 0. Right? So basically what happened over here is, if we try to draw a circuit diagram for this, basically t equal to 0, our output was everything we set it to clear. At t1, we had 1 0 0. T2, we had a right shift of this one. T3, we had one more right shift. And T5, it became again one came in the beginning. Right, now if we have to draw a wave diagram for this, let's assume that we have multiple clock edges. Let's assume this is our first clock edge. This is like time 0. Let's assume T0. This is T1. This is T2. This is T3. And this is T4. Right? How would we represent? So basically, what are these? These are nothing but QA, QB, QC, and QD. Based upon the previous diagram, these are QA, QB, QC, and QD. What would happen in this particular case is, right, say at time t equal to 0, before this our clear was equal to 1, we made clear equal to 0 over here. Let's draw it a bit neatly. Something like this. We had this is example of a clear. So this is a level 1, this is a level 0. Let's assume at time t equal to 0, we load a value at d, input of dA equal to 1. Alright, before applying a clock edge. Just before applying a clock edge, we made a value of d from 0 to 1. Now what will be the QA, right? QA, if initially it was 0, at time t1, it will get a value. Okay, so basically what would happen over here is, let's assume this is a time t0, everything was 0. But what we did over here is actually we applied this particular d value just before it, say, right? So let's change it and let's look at our particular equation over here. Something like what would happen is QA at time t equal to 0, just before the clock edge, would be 0. Okay. So basically QA at this particular point of time, and time t1 it will become a value 1. Then again at every time it will remain 0 except for time t5 where it will again become 1. Similarly QB would be equal to what, it will stay 0 till the time to t2 become a t2, come down at t3. QC would be equal to, so basically this particular edge corresponds to this particular edge corresponds to this, right? And similarly QD would be something which will get high at, this is t4, this is t5, this is t3, this is t4, t2, t3, this is t1. Correct? Now this particular diagram, this particular wave diagram is the one where we say that this particular example is an example of ring counter. And what you see over here is, right, what we have achieved over here is this circuit is nothing but a divide by 4 circuit. If you look at it closely, right, what is happening in this particular case is, let's assume this was our clock frequency, initial clock frequency, and this clock frequency was this clock period, right? This was the clock period. Now what is happening in this particular case is, right, our clock period has reduced by a factor of 4, right? T1 will go high over here, the clock factor has get reduced by, so basically this is 4 TP. So this particular circuit is known as divide by 4 circuit, or this is also called as modulo N circuit, right? This is the nomenclature we use, and basically the property of ring counter is, depending upon number of flops in the circuit, that circuit would be useful for achieving a frequency of modulo, that particular modulo. For example, we used 4 flip-flops over here, so this is a divide by 4 circuit. If we use 3 flip-flops, it will be divided by 3 circuit. 5 flip-flop, it will be divided by 5 circuit, right? And in that case, if we have to get a circuit which is like a divide by 10 circuit, right, what we will have to need is, we will need a 10 flip-flops. Correct? So this is one of the example of ring counters. Let's look at one more variation of this particular counter, and we will rename that particular counter as a Johnson counter. Johnson counter is nothing but this is same variation of a ring counter, where we have, let's assume this is like a 4 flip-flop circuit, where instead of connecting Q, we connect Q bar to the input, right? If this is a particular case, let's assume this is D, this is Q, this is D, this is Q, D, Q, D, Q. What would happen in this particular circuit, right? Let's assume this is QA, QB, QC, QD. Let's assume all of them have a common clock. They have a proper clear also, like we discussed previously. They have a proper reset, that so that we can reset it at time t equal to 0. Now what would happen in this particular case? Let's assume we have this QA, QB, QC, QD. If at time t equal to 0, they are all 0, what will happen at a time t1? Since this particular, let's assume at time t equal to 0, we clear, or basically we reset the signal, it's all 0. Now at time t equal to t1, what we do is, this particular D, so basically this was 0, this was 1, this came as 1. At the next clock edge, QA will appear as 1. At next clock to T2, this is also 0, so 1 came over here, so it will become 1 1 0 0. At time T3, it will have 1 1 1 0, right? At time T4, we will get all ones. Now 1 is here, output at the next clock, so basically if 1 is over here, output of this will be 0, so basically 0 is present over here, and in the next clock edge, that is T5, 0 will come back, right? 1 1 1. What will happen at T6? Again 0 will come to the front, the output would be 0 0 1 1. T7 it will be 0 0 0 1. T8 it will be 0 0 0 0. Then at T9 it will again write 1 0 0, and this cycle will repeat. Correct. So this particular variation where we connect q bar to the input is called a Johnson counter, and this Johnson counter has multiple advantages over ring counter, right? The first advantage of Johnson counter over ring counter is we don't need to preload input of Johnson counter, right? If you remember in the previous ring counter, what we had to do was in the beginning, right, before time t at t equal to 0, before we start a clock edge, right, we had to load a value of 1 in order to ensure that the value of 1 is transferred at the next clock edges and the circuit just moves on from there. But in this particular case of Johnson counter, since we are connecting q bar, if the initial state is 0, this q bar would be 1 at the first edge of the clock at time t1, and qa will get a value of 1. So basically we don't need to preload. Now the second advantage over here is, right, if ring counter is modulo n, Johnson counter is modulo 2n. We will see what this means through a wave diagram, but to give you an idea, right, this means that we can obtain same function using a Johnson counter. We can obtain the same function of a Johnson counter, right, of that of a ring counter by using half flip-flops. So basically flip-flops required for Johnson counter is equal to flip-flop required for a ring counter by 2 for the same operation. And this is a huge saving. So basically if we look at it, right, how do we look at this? So basically we drew this particular table, right, state table. Now let's try to draw a wave diagram for this particular state table. Let's assume that this is our clock. I am taking more clocks because we have multiple operations over here. So let's assume this is a time t1, t2, t3, t4, t5. At time t1 what we had was 100, right? qa, let's assume qa went to 1. Let's assume clear was applied before this, right? So all the clear operation happened. So basically what would happen over here is qa goes 1 and qa remains 1 till what? Till the time t4, and at t5 it will become 0. Correct. So for 4 clock edges it will remain 1, and at the fifth clock edge, right, it will go to 0. And then it will again go to 1 at t9. What will be the operation of qb? QB would behave like QB became once at T2 and it will remain 1, right? It will remain 1 till T6. At T6 it will become 0. So T2 to T6 again at T10. QC similarly we go up at T3 and remain 1 till T7. Correct? QD high at Q4 comes back at T4 and it comes back at T8. So now what is happening in this particular case, right? In this particular case, let's assume the clock cycle was T, What is the clock cycle over here? It's 80. So basically what we got is we got divide by 8 circuit using 4 flip-flops. If we have to do obtain a divide by 8 circuit using ring counter, what we had to do was we have to use 8 flip-flops. Correct? So this is what I meant by modulo n and modulo 2n. Right? And one other thing about Johnson counter over here is in the Johnson counter, right, we are getting a duty cycle of exactly 50%. In ring counter, we were not getting it to be 50%. Correct? Similarly, what happens is if we now use a three stage, like for example, if we had a ring counter with 3 flip-flops, right? What kind of a circuit it would be? It would be divide by 3. What kind of a circuit would be Johnson counter? It would be modulo 2n. This was modulo n, right? This will be modulo 2n, so it will be divide by 6. What this would mean is if we are inputting a clock frequency f output would be f input by 6, correct? And it would simply mean that it would generate a 120-degree phased waveform, that is like 360 by 3. So this is an example of a Johnson counter, and these are like two special kinds of counter which I wanted to cover in this particular lecture, where we used some concept of shift registers coupled with synchronous counters. And what we did is we created a feedback loop when we connected QD back to the input D and preset to a value, loaded with the value. What we said is it's a ring counter which is a modulo n counter, and we saw a variation of this particular counter where instead of connecting a q of the last flip flop to the D of the first flip flop, what we did was we connected Q bar, and when we did so, what we got is we got a modulo 2n operation, whereas like basically number of flip flops required to obtain the same function of that of ring counter would be half. And then we drew a wave diagram to see how this operation is handling, and we saw it was like a 50% duty cycle and divide by 8 circuit using 8 flip flops. Hope this was clear. Thank you for attending this particular lecture.